Welcome to the start of this A-Level Maths series. The aim of this series will be to break down many of the complicated topics in the AS and A-Level Maths course in a way that covers all the exam boards. All of the notes that I create throughout this series will be available on my website, which is linked in the description, once I have completed them. A lot of you may look at the first few topics and think that you know them already from GCSE, and you probably do have a good understanding, but I would still recommend taking the time to fully master them because they lay out the foundations that will help you throughout the rest of this course. Thanks again for watching, and let's get into topic number one. Topic number one is proof and mathematical communication. Here are the 5 subtopics we're going to be covering within this episode, so let's get started with topic 1.1, mathematical structures and arguments. Now we've got some key points on the left hand side. An equation is only true for certain values of x. For example, 3x equals 6 is only true for x equals 2. And you could think of many other equations that also have this property. Only a certain set of values will make the equation hold true. An identity, on the other hand, is true for all values of x. For example, 5x plus 2x is always going to equal 7x, no matter what that x value is. The bottom two you may not have seen much before, but P arrow Q is read as P implies Q, and is kind of used when you're doing proper mathematical reasoning, and is sometimes used especially at a higher level of maths. Likewise, you can have it the opposite way around, so P arrow towards P from Q is read as P is implied by Q. Obviously, you could flip those around so that Q implies P and they mean the same thing. The bottom one is P is equivalent to Q, effectively, and this is read as P is true if and only if Q is true. Don't worry so much about the bottom two in terms of exam questions because they are a bit rarer, but always good to know about. So let's have a look at the first question I have as an example. Find A and B in this situation. You might recognise this from some of your GCSE studies. It is an example of comparing coefficients. So if we go ahead and expand that double bracket, just by using the claw method, we can first of all expand out the double bracket, which you can do in 2 steps if you want to, but with enough practice, we can do that in one go, x squared minus 2bx plus b squared. If we use the claw method to expand out this bracket now, so x cubed minus 2bx squared plus b squared x, and then plus ax squared minus 2abx, and then plus ab squared. Now, this is where the comparing coefficients comes in. So what is handy to do here is just collect up all the different x terms that we have. So x cubed is a standalone. As you can see over there, the x cubed, nothing changes with that. If we look at the x squared terms next, we've got one here and one here. So we can collect those two and have a minus 2b. Hopefully that makes sense. And then we've got the x terms, so the singular x terms, which we can collect up. We've got b squared. And we've also got a minus 2ab. And then finally, just the single constant terms, we've got ab squared. Now, in theory, we have 3 equations that we could make up here as comparisons. So we know that the coefficient on the x squared term is a minus 4. So our equation number 1 could be a minus 2b equals minus 4, because we're comparing this expression with this minus 4 here. Hopefully that makes sense. Likewise, we can do the same with the x and the constant term, so I'm just going to write those out. We've got b squared minus 2ab equals minus 3. And finally, this constant term at the end, ab squared, is equal to positive 18. Now, again at GCSE, a common way to do this would be to eliminate one of the equations really and solve simultaneously. It would be quite a high level simultaneous equation at GCSE level, but we're not at GCSE level anymore. Another trick that is one of those things that as you do the A-level course, little time savers like this will help you a hell of a lot. Number 3, the equation number 3, I recognised that this is effectively 2 things multiplied together, an a and a b squared, which make 18. Now if you think about the factors of 18, we've got 1 and 18, 2 and 9, 3 and 6, that's it. Now notice the b squared must be a square number, and the only square number in there is 9. Because of this, it must be 2 times 9 equals 18, where the a is 2, and the b squared is 9, so b must equal 3. Based off of this argument alone, something that I hope you do think about, b could also be a minus 3, so it is now best to look at the equations 1 and 2 to make sure that is not the case. So the easiest one to look at is going to be equation number 1. So if we substitute a is 2 and b is 3 in there, so that's going to be 2 minus 2 lots of 3, which is the same as 2 minus 6, which is minus 4. Now, if that was to be a minus 3 in the place of the b, they would become positive, and that would become an 8. So 2 and 3 are the only correct solutions in this case. Moving on to example number 2. Consider the square root of x squared plus 9 equals 3x minus 7. Again, not something you come across all the time in A-level papers, but they do pop up sometimes. We have to use those implied or if and only if arrows that we saw before. So to get between step 1 and step 2, what they have done here is square it. Because they've squared it, typically when you square something, it will be an implies, just one way. The reason for this is to use the equivalence arrow here, so the two-sided arrow, you would have to also prove that the right-hand side is always equal to the left-hand side, or always implies it. However, when we square something, to get to this, you could either square the 3x minus 7, which they have here, or it could be the negative version, and you would still get the same answer, so we cannot use the imply the same way backwards. Therefore, it is only the implies arrow to the right here. For the rest of these, it will be the equivalence arrow, because in every single step, there is no disambiguity between each of those steps. For example here, substituting x squared plus 9, they will always be equivalent because there's no special rules like the squaring rule. And then when you divide by 2, these two things are going to be equivalent, and obviously the 0 is always going to be 0 in that case. And that is how you'd answer the rest of those. As I said, they're not that common in exam questions, but definitely something to kind of think about and be aware of. Moving on to 1.2, and this is inequality notation. So again, at GCSE, you would have only ever seen x is less than 6, or x is greater than 0 and less than or equal to 1, just reading those first two off of this sheet. However, there are things such as set notation and interval notation for inequalities, and as you can see, the two examples here and here. Another thing to note down the bottom, which you would have seen at GCSE, is A union B and A intersection B, and there are a few points about those if you want to read them. Let's go on to the examples. So write these in set and interval notation. So I've left a good amount of space. We can do I and II as set and interval. So set, we basically just write the same thing, but inside these curly brackets, which are typically used for sets. And it just is a formal way of writing x is the set of numbers such that x is less than 6. Interval notation here, because it's x is less than 6, we're going to have a 6 on the upper bound with a rounded bracket, and that's going to go as low as minus infinity. And when we use infinity or minus infinity, it's always a rounded bracket, because technically infinity isn't a value, so it can't be including infinity, which is what a square bracket would be, as you can see in this example here. That is only going to be for numbers when it is a greater than or equal to or a less than or equal to. Again, pause at any point and try and do these before me and then use them to check. But moving on to 1b, we have again the set of 0 and then less than or equal to 1 with those curly brackets. And then for the interval notation, this is not going to be including 0, so we do a rounded bracket there, but it is including 1, so we do that square bracket. Same again for C, so x is greater than 5 or x is less than or equal to 0. We do the first one as its own thing, or using our union, x colon meaning x is such that x is less than or equal to 0, and then those curly brackets on the outside of each of those. And then likewise for this one, we would still be using that union. X is greater than 5, so 5 is going to be our lower bound here with a rounded bracket up to infinity, or x is going to be less than or equal to 0. So 0 is going to be the upper bound with a square bracket and minus infinity in there with a rounded bracket. And moving on to question 2, this is basically doing the reverse. So write each interval as an inequality of x. So this one is simply going to be x is greater than 2, but less than or equal to 8. Again, the arrows are denoted by the type of bracket on the outside. So for this one, x is greater than 0, but less than 10, and x is greater than or equal to 8. Now, because of that and or the intersection, we can combine those two, because if x has to be greater than or equal to 8, and between 0 and 10, we can say that x is greater than or equal to 8, but less than 10. And that will be our final answer here. Moving on to 1.3, disproving by counterexample. So a counterexample, as you can see in the blue box, is a way of proving something isn't always true. Now, as a side note, it's not usually possible to prove something is always true just using examples, but here you will learn how to prove something isn't always true using a counterexample. So looking straight into question 1, a good example of a question you might get is something like this. So disprove by counterexample that this identity is true for all x. So this is literally talking about the idea that when you square a bracket, it is just the squaring of the individual terms inside it. Now we know that is not true because of the whole expanding a bracket, use the claw method, and you've got that middle term. So we could say something like let x equal 1, and it's always good to prove the left hand side, so LHS, 1 plus 1 all squared is the same as 2 squared, which is 4. If we do the same for the right hand side, you can see that 1 squared plus 1 is going to be equal to 2. 4 is not equal to 2, so it is not true for all values of x, and that will be your final answer. Number 2, prove that the product of two prime numbers is not always odd. Now typically prime numbers are almost always odd, and a good thing to remember is odd times odd always equals odd. Look that up, try a load of examples, you will find that is true. Now there is a loophole with prime numbers in that 2 is a prime number. So therefore 2 times 3 is 6, and you can do any example really. 2 times 5 is 10, but as long as you use that 2, you will be able to disprove this statement. And there are your answers. Let me know any others you might want to try down below. Finally, question 3. Use a counterexample to disprove x is less than 3 implies x squared is less than 9. So we need to show that for any number less than 3, applying it into x squared or squaring that number that you choose will not always be less than 9. A good thing to think of when you're thinking of these examples is positive numbers. So we can try for x is greater than 0, we can try that for x is less than 0, and we can try for x is equal to 0. When we're trying for an x is greater than 0, if you square that number, it's always going to be greater than 0. So let's say we went with 2, x squared is 4. If x is 0, x squared will always be 0. We don't need to show another example for that because there isn't one. If x is less than 0, then x squared will always be greater than 0. If we chose x equals minus 2, then x squared is going to equal 4. That does lie within this proof. However, we can go way below that and choose something like minus 10. If we square that, x squared is going to be 100, and that is much higher than 9, so therefore we have disproved that statement with a counterexample. It's good to get in the headspace of thinking about all the different types of x values you can have. Positive, negative, 0, odds, evens you will see in the next couple slides. All of these are very useful. Proof by deduction, another type. Now proof by deduction involves forming a series of logical steps to reach a final goal. Algebra is a very useful way of doing this, which again is something you wouldn't necessarily appreciate at a GCSE level, because they didn't really ask anything like it of you. Again, another good idea to think about. For any integer n, even numbers can be expressed as 2n, and odd numbers can be expressed as 2n plus 1. For those of you that aimed for kind of an 8 and above, you will be already aware of this. So prove that the sum of an even number and an odd number is always odd. An even number could be something like 2n. An odd number could be something like 2n plus 1, as we just talked about. Technically speaking, these are consecutive numbers. So if you wanted to be more robust in your proof, you could choose a different integer. So you could go with 2m plus 1 and 2n. You will still get the same idea as long as you follow the correct steps. If we take the sum of these, you get 4n plus 1. And remember, an odd number is when we double something and add 1 to it, because doubling something is always an even number. Adding 1 will always be odd. So here we can write 4n plus 1 technically as 2 lots of 2n adding 1 to it. And that is perfectly fine because we're taking the thing, doesn't matter what that number is, we're doubling it, which makes it even, adding 1, therefore always odd. Now this proof is slightly harder, probably the most advanced one we've done so far, but again a good example of what they could ask you. Prove h is given by this equation here. We've got a right angle triangle, we have a and a b, and a unknown h in the middle. Now the first thing we can do here, because these are right angle triangles, we know that a squared plus b squared equals c squared. Pythagoras' theorem, you would have learnt about it a long time ago. We can use this to get an expression for that bottom base of the triangle. So using Pythagoras' theorem to effectively find our c is going to be the square root of a squared plus b squared, and that is going to be that bit in there. The next thing we do is think about the area of a triangle. A equals half base times height. Now, we can either flip the triangle on its side so that the base is A, and how I mean by that is this little diagram like this, so that you'd have the area is half A times B, because that's your new base, that little A there. Or we could have that the area is half the new base that we just worked out using Pythagoras, multiplied by the H, which is the actual height. So that would be half times the H times by the square root of a squared plus b squared. By doing that, we have two equivalent statements here, and we can manipulate these a bit to get to our final answer. So straight away, if we multiply both by 2, we cancel out these halves. And simply by dividing through by the square root of a squared plus b squared, we get our final result of ab over the square root of a squared plus b squared. And that is our final answer. Sometimes you might find these proofs are signed off with a little square, and that just shows the proof is complete. So technically speaking, I could have done this for all of them. Again, just something that you're aware of in case you see it. On to our final subtopic of this lesson, 1.5, proof by exhaustion. So we've covered counterexample, deduction, and now exhaustion. All three very important to be aware of. Proof by exhaustion is somewhat similar to deduction. It involves checking all the possibilities. Might sound impossible, but there are lots of ways using algebra to do this. You will see some quite clever ways that will get slightly harder as we go through these questions. So question number 1, prove that 13 is a prime number. This one isn't too bad to prove because 13 is a small number, but going forward you might get some higher numbers, and the best thing to think about is if a number is not a prime, you will be able to write it as the product of its prime factors. So if there are no prime factors in a number, or no prime numbers that go into that number, it must be prime. So the only numbers we have to check for this are prime numbers. So does 2 go into it? No. 3? No. 5, 7, and 11. All of them do not go into 13. 13 and 1 are the only factors, therefore 13 is prime. And that is our final answer. Moving on to question 2. Prove that n squared plus 2 is not divisible by 4 for integers of 1 to 5. So we can just write out 1 to 5 first and have a nice layout. So n squared plus 2 if n is 1 is going to be 3. N squared plus 2 is going to be 6. N equals 3, we're going to have 11. N equals 4, we're going to have 18. And n equals 5, we're going to have 27. And as you can see, none of these are divisible by 4. You could prove this by showing that they all give a remainder of something that isn't 0. So the first one would be remainder 3, second one remainder 2, and so on. But that should be good enough as this is quite a simple example. And up here, something that is slightly more complex and will make you think a bit differently. Prove that n squared plus n is always even if n is an integer. This n is a member of the z, just means the set of integers. A good way to break up the integers into a manageable situation is you will always either have odd or even. You cannot get any other type of integer other than odd or even. And this is something that we know how to use algebraically, because we could say we've got 2n plus 1, or we have 2n. So if we imagine case 1, if we substitute 2n plus 1 everywhere that we see n in the expression, we're going to have 2n plus 1 squared plus 2n plus 1. And if we expand out that bracket, we're going to get 4n squared plus 4n plus 1, and then plus the 2n plus 1. And this is going to give us 4n squared plus 6n plus 2. And just like we did before, to prove something is always even, we can take out a factor of 2, because anything doubled is always going to be an even number. So that is that one proved. And for this one, we can just substitute 2n everywhere that we see the n in the expression. So 2n all squared plus 2n we have 4n squared plus 2n, and again take out a factor of 2, and we get this, and that will prove it. Anything doubled is an even number. And that sums up the end of topic 1, which is proof and mathematical communication. So thank you very much for watching. I really hope this is useful, and I really hope you can use this series towards your revision and to improve your understanding of any of the topics through this tough course. I promise it is worth learning it all, as hard as it may seem. But again, thank you very much, and I will see you in the next one.